In this section, we're going to be graphing some classic graphs that are polar graphs. The polar graphs we're going to look at, we're grouped into families, so types of families of graphs. So the four types of families we're going to be looking at in this section are constants. So what happens when you just have the radius equal to a constant, like radius equals 5, or theta equals a constant, like theta equals pi over 2, or theta equals 4 pi over 3. And then we'll look at circles, roses, and limacons. And the big thing in looking at polar graphs is remembering the symmetries that happen for cosine and sine. So you would have seen this in the exploration. So because cosines are odd functions and sines are even functions, we look for cosine graphs to have x-axis symmetry. So remembering that the x-axis is, in a polar graph, the x-axis is the polar graph. So cosines are going to have polar axis symmetry. And the sine values exhibit y-axis symmetry, which in a polar graph is the line theta equals pi over 2. So knowing these symmetries and then grouping our graphs into these families can help us know the shapes and help us to graph them more easily. So again, just remembering what symmetry looks like, right? Here is symmetry, and it's symmetry about the line pi over 2. So that's this line right here. So there's the axis of symmetry, and you'll notice that every point that's plotted on the right has a mirror image on the left, right? So if I plot a point over here, then there's a matching point over here. And what that means when I have this symmetry is that instead of plotting all the points, I could just plot points from here to here, right? From minus 3 pi over 2 to pi over 2, and then I could flip or reflect those points over the line theta equals pi over 2. And remember that anything that has a sine is going to have this kind of symmetry. Then we have what's called symmetry with respect to the polar axis. So it's kind of like the x-axis, right? There's the polar axis. And again, what that symmetry means is that any point that I plot underneath, there's going to be a matching point on top. So for the most part, it means that all I have to do are find values between 0 and 180, and then I can reflect those points over the polar axis. And remember, these graphs are going to be all of your cosine graphs. There's also symmetry with respect to the pole, right? The pole is another name for the origin in a polar graph. We're not going to be spending a lot of time looking at symmetry about the pole because we won't be studying these particular types of graphs, these lemniscates, in this unit. All right, so here are our first kinds of graphs. We're talking about constants, right? So if I'm looking at this first picture, r equals k, a constant, right? I would have something like, this is the graph r equals 3. And you can see that it's just, where does the radius equal 3? And that's going to be a circle, right? Where the set of all points are 3 spaces from the pole. Or this graph, right? This is the graph r equals 2. Everything on this graph, all these points on this graph, all have a radius of 2, or are 2 spaces from the pole. All right, then you've got this graph inside. This is the graph r equals 1, same thing. So those make circles. The other constant graph that we look at make lines, right? So while this guy over here is making circles, anytime you have a constant value of your angle, theta, it makes a line. So for instance, theta equals pi over 4, right? That's a straight line, right? Making an angle with the polar axis of pi over 4. And you want your line to go all the way through. You don't want it to just be in the first quadrant that the angle's in. Okay, same thing over here. If I'm graphing the line theta equals pi over 2, the line itself is making a pi over 2 angle with the polar axis, and then the line's going to go the whole way. Okay, not just from the pole up. Okay, next family we're going to look at are circles. So circles always look like a leading coefficient and then cosine or sine. So r equals a cosine theta or r equals a sine theta. And a couple of things to notice. When we have a cosine, we want to notice that the polar axis or x-axis is going to act as the diameter. So both of these guys, right, are symmetric with respect to the polar axis. Okay. And then the second thing we're going to notice is that the diameter of each one of these circles is going to be a. So the leading coefficient gives us the diameter. If a is positive, it goes in the positive direction, right? If a is negative, it will go in the negative direction, right? It'll open to the left. Then we can look at sines, right? So first looking at symmetries, right? The y-axis, or in this case, theta equals pi over 2 when we're doing a polar graph, acts as the diameter, right? We have symmetry about that line. So there it is there. There it is there, right? Notice our circles are symmetric. And then the other thing we're going to notice is that, again, the diameter is a. If it's a positive value of a, right, we're going in the positive direction for y. If it's a negative value of a, we're going in the negative direction for y. And that's just literally every other graph we've ever looked at, right? When you have a negative leading coefficient, it flips the graph over its axis of symmetry. So let's look at some examples for circles. All right, first one, graph r equals 3 cosine theta. So a couple of things that we want to notice. Number one, this graph is in the circle family, right? Because it's a coefficient times a cosine or a sine. Second, this graph is a cosine, so it's going to have x-axis or polar axis symmetry, right? So I expect it to look something like this, right? Next thing is the diameter is going to be equal to 3 because the leading coefficient here was 3, right? So remember this guy right here is going to be the diameter. And then last thing, this graph is going to open to the right or in the positive direction, right? Because the leading coefficient is positive. So when I graph this, you can make a table of values. Remember that because it's symmetric over the polar axis, you really only need to make values from 0 to pi, right? You really only need to make these values in your table because you'll notice that these ones right here are just reflections, right? All of these ones are just reflections. So we really didn't even need any of these values if we can remember that the cosine is symmetric over the polar axis. Right, and then you'll notice a couple of things like, look, there's the diameter, 3, right, and that it opens to the right because it was positive 3. All right, so next example, let's graph r equals 3 sine theta. So again, this equation is in the circle family, right, and this sine graph will have y-axis symmetry, right, or theta equals pi over 2 symmetry. We still have a diameter of 3 because the leading coefficient is 3. And the graph will open upward because we have a positive leading coefficient. So we're expecting our graph to look something like this. So we would make a table, right? But if this is the axis of symmetry, then the only table that I really need to make is I just need to find the values between 0 and pi over 2. And then we'll notice that everything is reflecting over that, right? So like here are my values between 0 and pi over 2. And then notice that these values are just reflections. Okay, so we really don't need any of this. As long as we can remember that the sine circle is going to face in the positive direction. It had a positive leading coefficient. We'll notice that the diameter is 3, right? And then it's going to be a symmetric about the line theta equals pi over 2. There it is right there. All right, you give this one a try. This is guided practice number 1. Can you graph r equals -4 cosine theta? So remembering that this guy will be a circle, that it will have a diameter of 4, and that because it has a negative leading coefficient, we would be expecting it to be going in the negative direction. So that rules out this one, right? These ones are sine graphs, right? Because they're symmetric about this line. And that means that our only choice is B. All right, next family. Let's take a look at limaçon. So limaçon is a French word. That's why you have this fancy French letter here, right? And it's the word for snail, and it actually was named by Blaise Pascal, the guy who made Pascal's triangle, because he thought that they looked a little bit like snails, like a snail shell. All right, so as with other polar graphs, we want to remember that cosine is going to give us x-axis symmetry or polar axis. And sine graphs are going to give us y-axis symmetry or theta equals pi over 2 symmetry. So these graphs look like a plus or minus b cosine theta. So all it is adding, in addition to having a leading coefficient of b, it's adding a constant a. And you could see like a plus b or a minus b, and then we'll look at the different cases of how they make these different shapes. So cardioid is kind of like a heart. Then you have like what's called a one-loop limaçon, and then an inner loop limaçon. And these things happen when the different values of a and b are in relation to each other in different ways. So let's take a look at some of those. All right, first one. If A and B are equal to each other, you'll make a cardioid. That's a heart-like shape. Okay, so then the outer loop will have a diameter of A plus B. So if I'm making my shape like this, right, there's my heart. That's not a very great heart, but good enough, right? And then this will be the diameter from the cusp. The cusp is where it starts to turn in, right here. The cusp will be at the pole. That will be the pole, and then this will be A plus B. Okay, and then if A is greater than B, we'll have what's called a dimpled limaçon. It looks a lot like a cardioid. It will be probably difficult for you to tell the difference, really. But we'll still have an outer loop, right, like this. And the big difference will be, instead of having the cusp at the pole, the cusp will be at B minus A, and then we'll measure the diameter out, and it'll still have a diameter of B plus A. So how are these different? This one is at the pole, whereas this cusp is at B minus A. Okay, let's take a look at some of these. All right, so the area lit by two lights that shine down on a stage can be represented by the equation R equals 1.5 plus 1.5 sine A. So I want to immediately recognize that this is going to be a limaçon of some kind, and then see what can I say about A and B. That'll help me graph it. In this case, I notice that this is a sine function, right? So I'm expecting it to be symmetric about the theta equals pi over 2 pole. So it's going to be symmetric about there. Okay. And the other thing I notice is that A and B are both equal to each other, right? Here's A and here's B, and therefore this is going to be a cardioid. So since everything's positive, I expect it to go up, right? I expect the cusp to be at the pole, and I expect the diameter, that's this guy, to be A plus B, or in this case, 3. Okay, so that's what I think it's going to look like when I graph. If I plot a handful of points between negative pi over 2 and pi over 2, so remember, I only have to graph between here and here because everything else is going to reflect over, I get exactly what I expected to see, right? I get that the cusp is at the pole, and I also get that I have a diameter of 3. So in this case, if I'm trying to answer the question here, The polar pattern indicates the lights will light up a large portion toward the back of the stage, right? So here's where all the lights are going to be, in the back of the stage, and really not that much light at the front of the stage. All right, last example for limacons. If the absolute value of A is less than the absolute value of B, then we get what's called a one-loop limason. And that means we have this little inner loop, this little guy in here. Okay, so we have two loops. We have an inner loop, and then we have a big outer loop. And the rules are that one loop will have diameter B plus A, and one loop will have the diameter B minus A. And whichever value is smaller, obviously, is the smaller loop. And then the cusp will be at the pole. And this guy right here is the cusp, right, where the loops overlap. So let's graph 1 minus 3 cosine theta, right? This is a limason. Because this is a cosine, right, we're expecting to have symmetry with the polar axis, right? So we only need to find values between 0 and pi, and then we can just reflect them over the polar axis. And the other thing we notice is that because the value of A is less than the value of B, and when we say A and B, we mean the absolute value of those. So like here, I have 1 is definitely less than 3. So this will be a limason with an inner loop, and the loop diameters will be A plus B, right, which is going to be 2 in this case, and the negative just means it's going to face left. And then A minus B will give us a diameter for our outer loop of 4. And then, of course, the cusp will be at the pole. So here's my table where I'm plotting points, right? 0 through pi. That's all of these points over here. That's all of the points on top, right? And then what we've done is we've just reflected all of these points down to the bottom, right? All of these points can reflect down here. And so my loop values, right? This loop has a diameter of 2. Here we go. This guy has a diameter of 2. And then, of course, my outer loop has a diameter of 4. And the cusp is at the pole. All right, so let's try example 3, guided practice. Let's use symmetry to graph 1 plus 2 cosine theta. So again, this is a graph where A is less than B, so it's going to have an inner loop. My loops are going to be 1 plus 2, which is 3, and 1 minus 2, which is going to be -1 or 1. And it's a cosine, and it's got a positive leading coefficient, so it should be facing off to the right. So this would be a sine, it can't be that one. This would be a sine, it can't be that one. Those ones both have pi over 2 symmetry. So it's either going to be C or D. This one would be negative leading coefficient, right, because it's facing to the left. So it has to be D.